Yeah, so it's nice to be here. Actually, it's first time for me to come to this institute. Uh, so so we all know that we live in a major change in computing, right? And the change has been very fast particularly in the last 20 years or 30 years. So just give you a picture of how quickly things changed. You know, when I was a student, most of your age, that's merely like 30 years ago. Think about it. And computer science was so simply classified. So this, when I was in CMU, are the four areas that we study, and we only have four classes. So those are also the name of the classes we took. And clearly, since then, the universe of computing just rapidly expanding from 90 to this century. And nowadays, I think most of the major conference, are bigger than the entire computer science. So this is just how massively everything grows. Of course, the change is not just because of the power of computing rise or the power of communication rise. In some sense, probably in my mind, the biggest change is that the discipline of computing greatly expanded, essentially touched every corner of the society and touched every discipline. And this interaction introduced many new problems into computing and fundamentally challenged the framework of computing and greatly expanded its possibilities. So all those new applications each time come in, they shaken our uh, framework about what is input, what is output, and the model become more complex, and the computational problem become much more expensive. So periodically, it forced the fundamental element of computing to examine itself, to go beyond the traditional thinking. Right? So because the new problem, new framework, new computational model arise. So many people often say that the revolution in information and computing are driven by big data. Right? That's usually people say because big data really forced the computing. But in fact, big data has been there for a very long time. So, for example, when I was a student, uh, people are working on many big data. One particular example, beautiful example, is chess program. So if you look at the chess data, it's big data, right? All the possible configuration of chessboard that can be reached from beginning. And even von Neumann was so interested in that, he did an estimation, the live chessboard, the one that can be reached from beginning, is approximately 10 to the 46. So basically, big data has been there. And in fact, for example, throughout the 80s and 90s, a lot of the early work that pushed to today's computing are somehow derived from the desire to handle this sort of implicitly generated big data, right? Chessboard is nice because you can generate them. This data is implicitly given to you. You can create those boards, but it's just so many. So, so during my days at CMU, uh, as I said, we have four classes, and one of the classes that the furthest away from me as a theoretician is AI. And the CMU professors are really smart in such a way that they all together work together to teach one class. So the single AI class is taught by the entire AI faculties. And when I look back of my professors back then, there's already like 4 Turing Award winners on this list, and probably later on will grow. However, the person who impacted me most are not the 4 Turing Award winners on the list. It's a man which I put down his name. His name is called Hans Blin. Right? So many of you probably don't know who Hans Blin is. He's actually a very famous man in the following sense that if you go to the Science Museum, for example, in Chicago, they have a section called computing. There's only one picture there, is him. Because he designed the first chess program that reached to the master level. This chess program. So in some sense, he's one of the first few people handle this big data, like this the chess data. He designed the first program that reached the master level. He himself is a remarkable chess player. He used to be the amateur champions of US. So he's a deeply endowed with knowledge of chess, and then he's in the field of computing and AI. So this is why he can push for this program. So in fact, in my class, he's the first professor took the stage, and he taught for a few, I think, maybe 3 weeks lectures. And in his lecture, basically, he presented many of the techniques to search for the chess program. So on the AI, it's called search. That's a subject called search. So many of those techniques are quite familiar today. He started with BFS, we all know, BFS. And then gradually, he began to introduce some other search techniques. And today, often know A star, B star, any letter with a star, which give you somehow more clever way to search this chess tree and essentially embedded in his this chess program. So then clearly many students, after listening to our search program, they began to ask a question to say, Professor, why A star is better than B star or DFS, right? People began to ask, why particular new techniques? They all seem to be quite ad hoc, but why is better? So he gave a very beautiful answer at that time in my mind. He somewhere just suddenly said the following phrase: "Intelligent heuristics are the future of computing." He just popped out of this sentence, and somehow this sentence caught my attention. I didn't ask a question; somebody else asked. He just replied, and so I was deeply impressed by this sentence because of the following: that I am being trained as a theoretician, and I always been told that algorithm and computational complexity are the foundation of computing. Since then, intelligent heuristics, what the heck are the heuristics? So, in fact, actually, at that time, I had even more struggle with this concept because in my TOEFL GRE test, this word didn't show up. So I don't know what's the meaning of a heuristic. Never see these words before. But when he teach, somehow I kind of get the sense of what it might be. Right? So after class, I asked the professor, "What are heuristics?" I hope he gave me a definition. He didn't. He didn't detect that I don't know this word. So he just went on and gave me an explanation why heuristics are important. Right? Clearly, it's because data is big. You have to use the heuristic. That's essential language. So shortly after that, I got even more confused. I decided to ask a cohort students. So we have a really smart student from Taiwan, and his name is Fengxiong Xu. So at that time, he was study parallel architecture and VLSI design. So he decided to use parallelism to design another chess program. So Fengxiong himself is not a terrific chess player. He's just an okay chess player. Unlike Hans Bliner, who is himself like champion player. And his program began to really take step because he used parallelism so he can search much deeper into the game tree. And eventually he called this program deep thought. You can think deeply, deep thought. So his program called high tech. And in my final years, these two programs were the final two computer chess program in competition. And you all know which one students are rooting. They all root for student program to defeat the professors. So that's the year Fengxiong's program actually beat over the high tech. So it's the first computer program defeated the Hans Bliner's program. Okay? So Fengxiong Xu, of course, later on moved on to IBM and developed IBM Deep Blue, which defeated the world champion. Right. So clearly, this is a major player in the computer chess program. So I asked him, what are the heuristics? he thought about it because he also speaks Chinese. So I told him I don't know the words. So he explained that essentially he gave me this answer, the approach that works well in practice. And then, still not satisfied, I went to a theoretician who writes great programs and who is a great theoretician. His name is David Applegate. And he gave me, perhaps at that time, an answer, making me think a little bit more. He said heuristics are something intuitive, namely has some foundation, but effective, like what Fengxiong said, however, without theoretical guarantees. Right? So that's to the degree I began to understand these words which I never studied. And I think, like many of you, I was young when I was in my early 20s, and I have a relationship. So that evening, when I was having dinner with my girlfriend, who is an architect, and I was explaining to her about this concept of heuristics. So I drew on the napkin some pictures, and here is a kind of sketch of that picture now. Essentially, I try to describe, this ideal world, and people are fascinated by this practical world. And they saw a kite flying in the sky. And the people in this ideal world basically, wow, look at that kite, just a little thread holding it, and there's nothing happening, and it's floating. It's beautiful, right? So it is really beautiful. And someone on this world, this ideal world will say, well, if you watch long enough, the kite will fall. Right? So that's almost like theoreticians justify heuristics. In the worst case, they never work. Right? The kite will fall off the sky. So that's, I finally feel, well, heuristic is just like this kite. Eventually, from our theoretical perspective, they have to fall. Right? And so next day, I was happy now, and I went to my the writer Gary Miller's office. I told him that I'm so lucky that I study algorithms, not heuristics. And I thought that he might just give me a big hug and to say, good student, you finally learned. But he didn't. He thought for a little while. Then he said, the randomized algorithm are somewhat heuristic. So that's all he's answered. And so nevertheless, what are heuristics become a thing in my head. I tried to somehow understand it. And in the subsequent years, 3 examples somehow emerged in my interaction and making me thinking more about this subject. And it's impacted my career. Okay, so the first one is a CMU work by a professor called Randy Bryan, and this is a work actually most cited before internet. So this work goes as following: they want to do model checking, so they need to express the Boolean function, and they just write down Boolean function as a tree. They call it decision tree. And of course, trees are huge, exponentially sized, and they try to combine them in such a way to make it small enough. And this is called BDD, binary decision diagram. So it sounds totally trivial in my head as theoretician, because many people are doing the same thing. But then they began to introduce a variety of calculus in this data structure to support many tasks in model checking and circuit design. Okay, so they have their own theory to say under what condition this BDD is effective. Okay, so that's the paper. He gave a talk. My office mate was his students, so I went there. But I was very impressed by his talk, even though in my head the kite will fall. Yeah. So same to verify. You have to verify the design is correct. Yeah. So basically, it's but the theory sounds like something disciplined, right? So this is the first time I had a glimpse of something has some kind of discipline, even though in the worst case the kite will fall off the sky. And so those days in CMU, all theory students had to write the programs. So I actually wrote the program for my PhD thesis, which is a geometric partitioning. And my program was so beautiful, it created this beautiful pictures that MATLAB, MathWork, even incorporated in their 92 calendars. and my name was even printed in this calendar. So I was very proud of my little program and the people use. But this program suddenly, because they sent out this calendar everywhere, to NASA, to Boeing, to everywhere, Intel, then I got the invitation to give talks because people saw this calendar. And so then I decided in '93 spend the summer at NASA, where they want to incorporate my partitioning program into their fluid dynamics package. And there I realized in their parallel computing, you have to decompose the computational meshes into components and you put it onto different machines. Right? That's basically the load balancing task. And they use another technique called the spectral partitioning, not really widely used in both in data mining and machine learning and so on. And so essentially they encode a graph into matrix, and then they take eigenvectors, and to reduce the search space from 2 to the n to n. Right? Andre just gave a talk to say partition cut has exponential size, right? But when they search, they reduce that to a linear size. Basically, they just scan through one of the vectors of this matrix. I'm not going into great detail because that's not my main point here. And so this clearly is a reduction of search, right? Effectively reduced from 2 to the n space using a numerical technique to a linear space. And this striking me as clearly a heuristic, right? To throw out so many solutions and just search in a narrowly defined domain. Okay? So essentially, it has a lot of mathematical intuition and physical intuition. It's built upon heat equations and the early work using quadratic programming, and there's a variety of early intuition built. For example, the famous one is Chigger's inequality. Right? So later on, I will touch a little bit. I use them as an illustration, not as a technique right now. And however, just like all heuristics, that the kite will fall off the sky. So in the worst case, it won't find a good partition. Okay? So that was essentially established everywhere, but it's widely used in practice. So this provides me one of the second example to say, this looks so disciplined work, even though it can fail sometimes, it's widely used in practice, right? So this is my definition now gradually. This looks like heuristics, right? With intuition and with no theoretical guarantee. Okay, it's used widely in scientific computing and VLSI at that time. So while I was working at NASA, my host, Horst Simon, who is a founder to develop the spectral partitioning, because he used to write numerical solvers. So his package was used everywhere in the world at that time. And he one day just tried to encourage me to think more about the spectral partitioning. And he said, if you look at all those experiments, they are really great. I said, I agree, because they incorporated my code to run side by side with their code. And we often stay within 5% of each other. But my code has theory. It has all the proofs that I worked so hard in my PhD thesis. And the spectral code in those settings always stayed within. But visually, they just look more beautiful. The spectral cut just look prettier. And, like art, you can't explain. They just look prettier. And I look at my own cut. I said, well, it's made into calendar, but it's not as pretty as a spectral cut. Right? So I was also drawn by the beauty of this cut. So Horst basically tried to encourage me to work, and he said something so beautiful. He said, there must be a theory to explain this. He himself is not a theoretician, but he highly encouraged, people like me to looking into it. He said, it works so well in practice, and you call it beautiful. There must be a theory behind it. It can't be just ad hoc. So shortly after that, I moved on to Minnesota to be a professor. And there, a few of my colleagues developed another partitioning techniques, which actually the first one defeated the spectral cut. So what they do is a multi-level method. Namely, they have a mesh graph. They gradually coarsen them into a smaller one. they try to build the quotient similar one. And they partition here, then they project down and do steep gradient descent. So that's heuristics. And this eventually beats the spectral cut. It just look and also perform much better. So this is the third example that I saw that potentially may have a theoretical background. And all of them actually essentially encourage me this question. There must be theory behind our work because they just look so good in practice. So in some sense, I want to use this example to inspire some of the explanation of theory work and how theory are derived from, like physics, right? You observe a phenomenon, you have to develop theory to explain it. And here, I think in the first part is also try to understand the heuristics. Then hopefully you can do more with your understanding. Right? So I'm not able to explain everything here. I will just give a sketch of the space. So the first attempt at that time to try is this spectral partitioning, and so clearly based on Shiger's inequality, one quickly mathematically try to think is how to understand eigenvalues, and because at that time what the spectral code is used mainly for planar circuit design, planar H graph, like circuit layout, and scientific computing, which is a three-dimensional, four-dimensional graph, right, if you have time. And so we began to first focus upon planar graph to see whether we can prove a theorem to say at least spectral partitioning is as optimal as any other techniques. So that's basically become a conjecture to try. And so in our attempt to prove the eigenvalue, we decide to do the heuristic way. So we take the first graph we understand. You can find on the book. This is normally when you say, what is planar graph? You draw this grid. And so this has simple eigenvalues. If it's a root n by root n graph, it has eigenvalue roughly 1 over n. Okay? So then we look at another graph we know, which in computer science, we do the complete binary tree. And if you do a simple proof, its eigenvalue, the second eigenvalue is also 1 over n after a constant, right? And these two graphs are so different because it's very short and this is long, right? This is kind of square root in diameter. This is like a log n diameter. And they all somehow get 1 over n in this eigenvalue. And so we said, let's do. Oh, I push it the wrong direction. That's the danger of. So then we said, let's modify this graph a little bit. And our old proof doesn't work. I think we can still prove log n over n at that time. And when we write the program for this eigenvalue, it's still 1 over n up to a constant. So this 1 over n somehow looks pretty magic for planar graph. As a result, we just began to guess that the second eigenvalue of bounded degree planar graph is also 1 over n. Doesn't matter, just planarity, just strong to give that. So it took the next 3 years, we finally able to use conformal geometry and so on to eventually prove this result. Okay, and this proof quickly expanded to three-dimensional geometric structures, and so this allow one to use Shiger's inequality, which connect eigenvector value with the cut ratio to argue, because Shiger roughly says the cut ratio, namely the pieces you cut out divided by the cut, that's cut ratio, is roughly square root of the eigenvalue. And if eigenvalue is 1 over n, the cut ratio will be 1 over root n. And if you look at this regular grid, it's precisely 1 over root n, because you cut off this is square root of n. You cut out the half n. So root n divided by half n is 1 over root n. Right? So you can see all those things eventually shows that these spectral techniques for this family reach to the optimal for that family, that class. And back then, all the theory for those class is just as good as the spectral cut. So spectral is actually optimal for that class. Right? So this is one of the first time we are able to derive a theory from those observations. And we were so excited at that time, Dan Spielman called this title, spectral projection works, right? So the people run for so many years, and now we are able to show they actually work in the setting of the meshes and circuits. Okay, so but understanding heuristics is not just field of us are thinking. In fact, my whole field in theory, people are thinking about it. So there's many theoreticians in the 90s began to look to expand the theory so that it can be much closer to practice, right? So in some sense, often blame our study of worst case analysis because the worst case kite will fall, but in practice, it's not that worst case, right? So that's gave a gap in theory and practice. So this is a report of a workshop in 1999, and you can see all those highlighted words are very close to the philosophy I discussed. Try to understand methods that work well in practice, but hopefully in a rigorous manner, right? And particularly, they highlighted the simplex algorithm for linear programming, simulated annealing, this steep gradient based method with temperature, very much like today's learning mechanism, and so on. So they want to understand on real data. They want to understand heuristics. Right? So this sort of broadly is a historical background for them. And so those days when we ask practitioners this question, why do you think practical data are easier? Of course, our initial question is even more stupid, which is tautology. So why do you think practical data are better than the worst case data? So this is tautology. Anything is better than the worst case data. Right? But somehow that's not how the practitioner read the question, right? So people give different answers. Some including the worst case are pathological, which often when we study NP reduction, dichotomy theorem, we often feel we build so much special gadgets, they are pathological. And then gradually you will hear practitioners say things are philosophically really closer to something like science. So some people began to say practical data are neither worst case and average case. So you will ask them why? Why it's not average case? And you will see, when you look at the bridge, it's not like average structure. When you look at the building, high rise, it's not average structure, right? Nothing is average. When you look at TV screen, a random average image is just a random screen, but our TV program immediately said it's not average, right? So, but it's not arbitrary. It's not the worst case, they say. And so you can see those quotes. The practitioner offer actually quite beautiful insight in what they consider to be a practical data. And particularly one of the friends suddenly said the following. He said, one way to say is neither worst case or average case, if you look at stock value, right? So for example, in China, it's Ali stock, right? It has a value. But this value, if you look again, it's different, right? So he said the stock value actually has two parts. One is market noise. That's why it keeps on changing. The other one is defined by the company, how strong they are. It gives you an anchor of a value, right? So this are man-made. The other one, the people of company couldn't even control, right? So basically, this suggests a potential numerical model of input is that every number is actually has two parts. An arbitrary part, which people can design, and a noise part that the nature just make you can't decide precisely, right? The nature could be market, could be physics when they do measurements, it's imprecise, or your uncertainty you had when you design, right? When people, for example, artists to draw the same thing twice, it will be two different pictures, right? There will be certain imprecision will be introduced, right? So at that time we went back to look at the most commonly used heuristic in computing. It's called linear simplex algorithm for linear programming, which basically solves this simple programming, maximize a linear function subject to a linear constraint. And when the linear constraint is feasible, it's polytope. And then you can have a starting place and you kind of gradient descent up to the climb up or down, doesn't matter max or min, to the objective function. And widely used in practice, great heuristics. Worst case is the exponential time. The kite will fall off the sky in the worst case. Okay, and so we incorporated this friend's suggestion of using stock value to model data to say if your program is indeed given by someone and they can't control a little bit of the noise. Right? So your linear program become this nature, this market noise if you're doing a sort of investment portfolio, right? This market will give you some noise. And then actually one can prove that the simplex algorithm runs in polynomial time in the input size and in the 1 over this standard deviation of this noise. So which means that if you have certain degree of uncertainty, the simplex algorithm are doing the right thing. They mostly run in polynomial time. It doesn't matter where your original design of the linear programs are, because that's not the one you're solving. You actually are solving a noise one, because when data come to you, it's the noise already incorporated. Okay, so this result began to take the field into a study of so-called beyond the worst case analysis. And for example, many of the practical heuristics which used to run in exponential time in worst case, then people can justify why in practice they never see it. For example, in data mining, the k-means method, when the point has a little bit of noise, quickly dropping in polynomial time. And one of the major one is that the local max cut, which is one of the typical example for local search. And this is a complete problem for local search. So this is the hardest local search problem. And that when the data has in the graph has a little bit of noise, is also dropping in polynomial time, right? So this, for example, theoretician has always think about heuristics. For example, in '85, when Johnson, Papadimitriou, Yannakakis introduced local search, polynomial local search, they actually remarkably write this sentence into their theory paper. Right? This sentence said practically all empirical evidence suggests finding local optimal solution is much easier than NP-hard problem. Then they went on to define this PLS complete. Then they said all problems are hard, PLS are hard. But the early result on local max cut basically say that is all polynomial time if we have certain degree of noise. So somehow justified this sentence, somehow embedded in their paper. So naturally, the phenomena go beyond just optimization. It can go to a multi-objective optimization, to learning, to game theory. So this kind of phenomena actually it's quite wide. That when your data are drawn from certain style of distribution, then often it's hard to see a worst case arise. So I will try to end my talk by going to some of our recent work from last year, and by come to some modern concept and another heuristic concept widely used in machine learning that I want to understand. So I will give you a little bit story how we went there. Is this I teach in Southern California. If you have never been to Los Angeles area, the one thing we have is beautiful weather. Right? How beautiful? Just think about in your city, the most beautiful day. We have that every day. So that's how beautiful the weather is. So I will show you a few pictures. We often sit outside. We rarely sit inside in there. And 15 years ago, we have a new colleague from Stanford came as a young faculty. His name is Shardin Dogmi. And he specializes in game theory and convex optimization. So those keywords you should remember because it's coming into the story. Game theory and convex optimization. So I took him for a walk. And then I asked him, do you understand machine learning? So this is 15 years ago. So you have to push back. At that time, today you don't ask this question anymore. Back then, do you know machine learning, right? And Shardin, not just brilliant, is also very straightforward. And He never hide something. He didn't know. He just simply say, I don't know anything about it. Right? So once he said that, I become much more honest. I also say, I don't know much either. Right? But it looked interesting. So then he thought about it, and he gave me a great answer. The next great answer really make me think he's a great thinker. So he said, it's not that I don't quite understand machine learning. Because many of the keywords I don't understand. Right? The keywords used in machine learning, I don't understand. That's what he said. Right? So clearly at that time, I said, give me an example. What do you mean a keyword you don't understand in machine learning? He thought about it. To my surprise, he said, regularization. Right? And I was there. I said, this is an expert in convex optimization and algorithmic game theory. What the heck do you know? You don't understand regularization? In optimization, you use regularization everywhere. Right? What do you mean you don't understand? It's not he doesn't understand the definition of regularization. He said, I don't know when people often use regularization in learning, how do regularization characterize the learnability? I can't connect regularization and the learnability, these two things, mathematically. He said, I don't see the connection. As a result, even though I know the definition, so what? Right? He said, I don't understand. So this become our research collaboration subject. So every day we meet, neither of us understand machine learning. We all know the definition of regularization, and we want to understand how it's used in machine learning. Clearly, it's a widely used heuristic in learning because it wants to overcome overfitting. Want to overcome overfitting. There's a variety of forms in practice, either as a function or, for example, some like drop off, some other noise injection. There's a variety of methodology are used. It's like black art used everywhere. But it's tied with a beautiful principle in learning called outcome research. So what is outcome research? It means the simplest model that explain are the best. This actually is what I love mathematics. Very often, mathematicians love simple proofs, right? Which is the right thing. You know, when someone give a complicated proof, you said, wow, so smart, so complex. But if someone give a really simple proof, then the mathematician, you are really smart, this is great, right? So people in this field intrinsically like outcome research, simple, that explain, right? Simple. It's a beautiful principle. So regularization to some degree, heuristically, that's how people justify why regularization is a good thing. Because traditionally, machine learning go with you want to minimize, find a model closer to the observation. You minimize so-called the error. And in the regularization world, what the conceptually thing is that every model has a complexity. Simple model, complex model. And when you want to fit your data, you want to both fit the data and also trade-off is model complexity. So this is a sort of broad framework of regularization. And so in some sense, philosophically tied with outcome research, right? Because if you minimize this, you take care of both the errors and also you try to find a simple model. So as a theoretician, when you do research, the most important thing is to create the conjectures. Even though the conjecture is wrong, they are still a step. If you know they are wrong, you make progress too. So two of us made our first wishful conjecture to say maybe under certain condition of learning that the regularization is universal. Anything that's learnable can be learned by regularization. So we step out, try to prove the thing, and we don't know anything about learning, right? So we said this is a good interest. And clearly in our mind, if it's true, it's a kind of formal proof of outcome research to say outcome research principle is universal. Okay. And so the framework, which often we consider in learning theory, in computational learning theory, will be initiated by Leslie Valland in 80s, and he defined this binary classification problem where you have data, you have labeled by 0, 1, for example, whether you're spam or not, your picture is indoor or outdoor, this thing, and you have a hypothesis class that produces labels. So he tried to tie with the complexity, how complex is the hypothesis class to learning. And his mechanism is the following, that he introduced two concepts, hidden. One is hidden distribution, one is hidden ground truth. So you have one member of here is the ground truth that produce label, and you also don't know the distribution. So then he said, well, the only way you can see this distribution is to draw IID samples. And then the ground truth will give you the label. And upon observing this labeled ground truth, then this is called supervised learning. Then you try to output a model. So he defined two kinds of output. One is called proper learning. You have to output the model in the conceptual class as your answer, or you can just learn whatever you want to learn. Right? Usually kids learn. We as a student, we learn this. We don't do proper learning, which often drive our professor mad, right? But it's a power of improper learning. So then he basically say, when they tie with the unknowns, he said, your job is to generalize, which is your ability to predict effectively in the future, that if you draw the data from same distribution, you want to be essentially correct. Right? So that's what he called pack learning. Right? Probably approximately correct. Right? So naturally, after he introduced this in the binary space, this quickly was expanded because one of the early projects in computer vision is to help the post office to identify handwriting. So they have 10 labels. They don't have just 2 labels. So you can think about the learning can have multi-class. And of course, today, when the label quickly go to infinity, right? Because, the face recognition, the label just essentially infinity. But the Valiant framework continue, right? All you need to do is replace this label space with its own geometry, and the rest are the same thing. Right? So this framework continues. So this will be the framework we consider called the multi-class supervised learning, or just called supervised learning in general. Okay? So learnability is very simply defined. That is, you want to see enough samples so that you can be essentially correct. Right? So this is called learnable. If you observe enough sample afterward, you will be essentially correct. How do you learn? And mathematically, it's usually modeled, say, if you see m sample, you can drive arrow to epsilon. It means that you can learn with m samples to this particular error. Right? So that's a more refined notion of learnability. And this basically is the sense of learnability. And unlearnable means that even though you see infinite samples, you still cannot learn. Right? So that's the divide between learnable and unlearnable. And then there's slightly different models. I will mention some of the difference. Right now, it's not that important right now. And so supervised learning is a beautiful framework because it captures the following philosophy. That is, you want to learn from examples, just like I learned heuristics, the concept from example. No one taught me what a heuristic is. I only saw some examples I need to learn. This is exactly the same principle. You see data, you want to learn. And you want to build a model so that you can generalize. However, it does not encourage you to remember. Right? So the name of the game is not to memorize, it's to generalize. Right? It's not memory. So it's a beautiful principle. Generalization is more important than memorization, which in education, that's our fundamental principle. Right? And it has a lot of application. Even in Chinese book, there's one of the story they talk about martial artists to learn sword techniques. The final answer about learn is how much you remembered. He said, I remember nothing now. Then he said, good, you finally learned, right? So memorize is not the name of the game. And it has many applications, including explaining how children learn their language, for example. And so in binary, there's a beautiful result, fundamentally done. Say something like a regular geometric dimension and half space. If VC dimension is bounded, you can learn just by gradient, just by ERM, which is proper. And it took many years for people to prove for multi-level there's a similar type of result. But the algorithm is very complex. It's no longer just go to the model. And it's no longer regularization. Why? Because people are looking for simple framework. Even though you can learn, is there a simple framework to learn? For example, simple framework is regularization, right? Unfortunately, that regularized learning is always proper. It's always output a proper concept. And in 2014, there's a beautiful result to prove in this multi-class learning, proper learning is insufficient. So which answered the conjecture which we restore that you can't just use regularize to learn. Regularization is not enough. Right? So this gave rise of our recent work to understand these heuristics with one motivation question is what is the smallest change that you can universally learn the supervised learning task? What's the smallest change to regularization? And so since I have small time, I will just go a little bit fast. The basic idea initially we want to go is to empower regularization to give it more information. The first step is allow regularizer to know the query point, okay? And that, unfortunately, is still not sufficient. You can prove just to know the query point, you cannot locally regularize. And so ultimately, we related with this broad domain called unsupervised data. So we're able to say, maybe you can allow it to read some unsupervised data to build a regularizer. So let me just be very quickly to state that one of the main results. That is, in the multi-labeled learning, if you allow to use unsupervised data and you allow learner to be randomized, then you can achieve optimality in learning. So optimize the learner using unlabeled data to regularize will be universal. So that's essentially the main result. So let me give you a rough sketch of this. I'm not going to overly go now because I have less time. Essentially, you can convert a learning problem into almost a bipartite matching problem. You can use this bipartite matching to kind of characterize learning error. Right? So today I will not overly do. And once you can do that, you can write a mathematical programming to capture what can be learned. And then we take all the solution, we maximize this entropy. So we call this entropy maximization. And this program, beautiful is that it has beautiful properties that we normally talk about. It has unique optimal solutions. It has strong duality and those things. More than that, the dual solutions is non-negative. And in machine learning, you have to understand, once you see non-negative, you immediately think about distribution. Non-negative things can be normalized into distribution. So essentially, the whole program after you solve is went as following. You take the unlabeled data, you build this program, and you can find a prior distribution by solving it. Take the due. And then you begin to see labeled data, you just do an update to a new distribution. This is just called Bayesian update. And then the learner just take this new distribution, somehow a hypothesis output result. That's all this is traditional Bayesian learner. And we show this framework is complete. This framework learn anything you can learn. So that is using unlabeled data to get the distribution. When the labeled data came, you update the distribution and you answer. So this is a complete framework. Namely, any supervised learning can be learned with this framework. And when you expand out this Bayesian update, it's actually locally regularized by KL divergence. So to give KL divergence explanation, it's just a local regularized once the unlabeled data occur. And simultaneously, it's also justify another principle often in learning called max entropy learning. That people in the past try to explain why max entropy is important in learning. So this proof simultaneously connects these three frameworks. And so I'm not going to overly down. There's many our concepts early on. They all fuzzy. They all heuristic, like learnability, local search, zero knowledge proof. But eventually, through theoretical work, they become much more crystallized. So in some sense, a lot of theories are trying to understand this, imprecise heuristic concept in the world. So this largely connects a domain called theory and practice. And clearly, this has been a theme for theory for a very long time. And this is a statement from Donald Cruz in '89. So, for example, it's beautifully written about why he cared about both theory and practice. Thank you.
Thank you for Professor Teng's presentation. Now we have some time for questions.
The fuzziness in the talk. So in some sense, a lot of the concept when it first arise, they are not, there may be a legal definition, but in practice, often they don't use that definition. For example, Morty Young is sitting here in crypto, that I think a beautiful concept is called the zero knowledge proof. And in some sense, proof, mathematicians are defined in a particular way. But broadly, proof has many meanings in society. For example, if you're a legal scholar, when you go to court, you also prove your case. I prove you're guilty, right? It's a different. Sorry. So, but it's different. But they also have the mathematical theory of what considered to be a proof of this statement, right? So just like when in crypto at that time when they arise in this domain, that eventually they have to say, how do I prove my knowledge to other? I know how do I prove certain statement that I declare I have knowledge, and without somehow disclose the critical privacy knowledge. So that's why, in some sense, they also have to rethink about what notion of proof is no longer this Hilbert logical. If A then B, if B then C, then if then A to C, right? It clearly went in a very different path, and then they are able to reformulate this enough. What I call the fuzzy concept. What is proof? It's not that precise anymore, right? If you talk with logicians, one thing, but if you talk about the common people, proof is a very different concept, and that concept is fuzzy. So that's why, in some sense, for people to go back to think about what is the right definition of a proof, I think in crypto eventually emerge in this beautiful notion of they may not be able to define partial knowledge proof, but they are able to define what is zero knowledge proof, right? So, and it's a rigorous mathematically defined in tie with computational theory and so on, right? Yeah. So this is kind of using rigor eventually to define and handle certain things far more further in our mind. A certain degree of, but everything has ambiguity. That's why what is good performance? Before it was not defined. Then theoretician comes in saying good performance. In the worst case, you have to be doing good. A student who should never fail, right? A student who cannot answer one question is a horrible student. That's the worst case, right? But in practice, people never think about that way. They said, a good student is the one answering many good questions, right? So you can see that theory and practice sometimes are facing this debate on what should be the right notion. Marty?
I will just comment how I motivate, especially to students, the connections between theory and practice, which you talked a lot about, and I agree with a lot of the things that you said. So in order to talk about theory and practice, I go back to Leonardo da Vinci, the start of the Renaissance and the start of the science, modern science.
Mm-hmm.
And he said two things, very, very, very interesting. First, he said, if you do practice without knowing the theory, this is like navigating a ship without a compass and all the navigation tools.
Mm-hmm.
Namely, you will get nowhere.
Mm-hmm.
On the other hand, he said, theory without application will soon die. So he saw very well the bidirectional connection between theory and practice.
Right.
So you see practice, you see something works in practice, you immediately need to explain it.
Mm-hmm.
And you develop theory, and maybe you go beyond the initial phenomenon.
You can give you a projection in the future. Yeah,
And
yeah.
then you
In
have to
unknowns. In the unknowns. Yeah, yeah.
Yeah, and you have to
Right.
project into future practice,
Right.
like AI.
Right.
So that's the full cycle, and it's already observed by Leonardo, who started all this modern science.
Right. And in some sense, if the detailed reading of Knuth's section, he essentially said philosophy. He said, sometimes I don't do theory because of practice. I just love theory. Sometimes I do practice without thinking about theory. But he said, they mutually nourish each other. That's essentially the essence which is beautifully written. So, right. Thanks, Marty.
Any more questions? Okay. So if there is no further questions, then let's thank Professor Teng again and thank all of you for attending.